first of the series today consists of data types and why you need to know them. And this is where we are. Data types is what determines the kind of tests you apply to assume or to come upon statistical significance will depend upon the kind of data you have. Second is how you represent your data uh, visually, graphically, or through figures will depend upon what kind of data you have. Now, if you were to ask me, I would put it down to two broad categories. One is categorical, also known as qualitative data, and the other is numerical or quantitative data. Categorical data are data that can be labeled, and they just have kind of a name, so which is why you call them nominal data. The other is it has a name, but you can order it in a way that it makes sense when you analyze it, that category 2 automatically follows category 1. Examples in the nominal data are, let's say, the infertility type, wherein you have azoospermia. You can actually count the numbers of couples who have presented to you with azoospermia. So let's say in a cohort of 100 infertile couples undergoing IVF at your center, you had 10 people with azoospermia, 20 with ovulatory disorder, 20 with tubal, and 50 with others. You would call this a kind of nominal data. In terms of ordinal data, you have parity can be considered an ordinal data, where nulliparity it would be followed by primary parity, and primary parity can be followed by multiparity. So that's ordered. In the previous example of nominal data, you don't really need your data to be ordered in any way. You could put your tubal factor first, azoospermia next, or ovulatory next, or you could decide to just kind of list it alphabetically, and that will not be will make any sense. So here, parity and the number of increasing children that a woman might have might affect outcomes. It might have a link with many other variables. Therefore, you have to make that distinction between nominal and ordinal. Within numerical are data that can be represented, that actually have a value. So that is numerical data, also called quantitative data. And even within this, you have two types, interval and continuous. So an example of interval data would be income levels. It could also be gestational age at birth. So you don't go about when you present your data, you don't go about mentioning 34 plus 5 weeks, these many women delivered, 37 plus 2 weeks. So you are ideally taken intervals. So 34 to 37 weeks, 37 to 39 weeks, and 39 weeks and beyond, and then less than 34 weeks. So that becomes interval data. Continuous data is where your variable can take any value. And a good example would be age not presented as intervals. It's actual age. It could be in days, it could be in months, it could be in years, or this is AMH, which is again an example of continuous data. There is also a third data type, which biostatisticians are aware of, and sometimes we as reproductive physicians also need to use it. This is known as time to event variable. It is simply put, it is the time that an event takes to occur. And for example, time to death or time to live birth, more relevant to us. It's a kind of a hybrid variable because it has a continuous part, which is time, and it has a binary part, which is an outcome, a yes-no variable, which is an outcome. So live birth, for instance, did it occur? Yes, no becomes a binary variable. So where will you encounter time to event variable in reproductive medicine studies are the ones that are cohort studies or RCTs. Retrospective studies cannot have time to event variable, right? So we'll leave it at that there. It's a more complex kind of variable to analyze and represent. Maybe we'll have a small segment on this later. So now you know about categorical and numerical data. Numerical data is again of two kinds, and you have come across words like normal, assumptions of normality, and Gaussian word. So these two are equivocal. Normal or Gaussian data, I'll be describing it in just a minute, or the alternative to that is skewed or non-Gaussian data. So this is what a normal or a Gaussian data looks like from your PSM studies. You probably have seen this several times. This represents the distribution of a continuous variable, wherein x-axis represents the values of the continuous variable, and the y-axis represents the number of times it occurs in your data set. So when you sort of plot it on what is known as a histogram, this is what you would get. You would get most values lying within the middle, a little bit lying to the left, and a little bit of the values lying to the right. So a perfectly normal curve is the one where you have bang in the middle, you have a value and values distributed equally on both the right and the left. Not just that, you would find that 95% of its sample will lie within 2 standard deviations of the mean. I'll be discussing standard deviation in a third module, but for now, remember that this is what, and it's easy visually to recognize that your data, if you plot it against a histogram or use a histogram to plot your data, it should look like this. As opposed to this, you have what is known as a skewed data. Now, skewed data, as you can see in the middle, represents normal data. There's no skew at all. And then when most of your values are sort of there, right there in the middle, but it has a slightly leftward skew, which is like a tail going to the left in the negative direction, that more values are now smaller in size and fewer values are higher in size, or in terms of values, that higher values are fewer. You call it a negative skew. Similarly, there is something known as a positive skew, where you have more higher values sort of still forming the tail to the right. So you have a right skew, which is a positive direction, and you have a left skew, which is in the negative direction. So how do you know if your data is normal or skewed? Most softwares, if you use them, will be able to tell you if your data is normal or skewed. Now, in our example, in reproductive medicine examples, papers that employ the variables of age and AMH, you'd find that this is how age is distributed, as shown in the left-hand panel. And to me, and to you also, I hope it appears more or less like a normal curve. So you have more people in the middle representing the mean, and fewer people on the left and the right representing an equal distribution on both sides. And this is what one would practically see as well in their clinics. With AMH, because we tend to kind of eliminate women with very low values from entering IVF, and sometimes our softwares are not able to pick up those the detecting softwares, the diagnostic softwares cannot pick up very small values of AMH. What you typically see is a skewed distribution of AMH, as the left panel represents. Now, there are tests, like I said, there are tests that can identify this. There's something known as a kurtosis coefficient or a skewness coefficient. And if this value lies between 1 and -1, you know that your data is normal. But if it is above 1 or less than -1, you know that your data is skewed. Now, why do you again need to keep sort of coming back to wanting to know whether your data is normal, categorical, skewed, not skewed, is largely because, like I keep saying, how you represent your data and how you compare your data are going to depend upon what data type you have. So we go to representation of data. Now, this was the two broad categories I had said that your data can belong to: qualitative categorical or quantitative numerical. Now, representation can be through figures or numbers, or they can be through pictures or graphs. So nominal and ordinal data can be represented by frequency percentage, which is basically a count. That number of people with primary infertility were 10, which were probably, let's say, 70% of your population. Similarly, number of people with secondary infertility were 3, and that constituted, or 4, that constituted 30% of your total population. So frequency, percentage, ratio, again, primary to secondary ratio, it can be presented as proportion and rate. And something similar for ordinal data, but when you have to represent it graphically, you use what are known as bar charts. And bar charts are not to be confused with box whisker plots. We will be talking in detail about both of these in our another segment. And quantitative data is represented through figures using the concepts of mean, median, or mode. The variance within its distribution is represented by range or standard deviation, and graphically, quantitative data is presented through use of histograms or box whisker plots. I think that's all for this segment.